Okay, howdy guys. So we're on Young's inequality, which is 8.7 in the book. Now, I want to note real quick that this is very much outside the scope of the class, the proof of it at least. Obviously, the statement's not because we're doing it, but the proof of it's outside the scope of the class. It relies on both Minkowski's inequality for integrals and the fact that it is, in fact, a special case of 618. Which is both of which are from chapter 6.3, and it is all of the multivariable Lebesgue, or sorry, the multivariable LP space stuff. So it's not necessarily within the scope of our class to prove it. However, the book does give a quick proof of the final inequality in it, and it is reliant on Minkowski's inequality for integrals. So I'm going to state part of that, the part that we need of that, and then explain what the book does for this. If I make a mistake, I do, with the explanation of Minkowski inequality for integrals, I do apologize. But this is going to, I didn't want to leave the proof completely out. I wanted to explain why this inequality actually holds. But before we get to that real quick, there are two things I want to state real quick. So within this proof, within Young's inequality, we have that if f is an L1 and g is an LP, p somewhere between 1 and infinity, then the convolution exists for almost all x. This statement here contradicts what I was saying, seemingly contradicts what I was saying in the last video, explaining how we know that the convolution always is well defined on Lebesgue measurable functions. At least when we redefine them using the oral measurable congruence classes that are given out by 212, Proposition 212. However, what I was saying when I was talking about that is I was saying that it is well defined when you have the integral mapping to the extended real line. So in other words, it might not be finite, but you can take the integral and be like, oh, it's infinity. And in that sense, it is well defined. So I'm not recanting what I said before, but I am putting it in context. So what this is saying is that it will actually be finite. And it's saying it's well defined on the real line as a real value function. I was thinking of it as a extended real line value function. And with respect to that, then you do get from what I was saying before that it is well defined for all of the measurable functions. Here we are talking specifically when it is real value, not extended real value. The one other thing I just noticed while I was putting the other video up online, I accidentally said that A was the Minkowski sum of the supports of F and G. When and visually on the board, I had written that it was the closure of the Minkowski sum of the supports of F and G. That is the correct one. I didn't mean to say that it was just the Minkowski sum, but it's the Minkowski sum, it's the closure of that Minkowski sum. So I just wanted to clarify real quick that what I had written is correct, not what I said. So going back to the proof, so we have that it is going to exist for all x's, for almost all x's. We have that the convolution is going to be an LP, and then we get this equality that the p norm of the, because again, it's an LP, so its p norm exists, and we're going to say that it is in fact less than the 1 norm of f and the times the p norm of g. Now, the proof of this is, again, these first two is a special case of 618. So we're just going to be focusing on this last part for the proof. And before that, we're going to need Minkowski's inequality for integrals. So it's a big theorem. I'm not going to state the whole thing, but the part that we need here is that if we have a multi-valued function a multivariable function x and y, where the measure on the space that x lives in is mu, and the measure that the space that y lives in is v. If we fix y and we range across x, and this guy is in fact going to be in LP mu for almost all y. And if we look at the function that maps y to the norm of this guy, then this is going to be an L1 of v. So if we have these two statements, are true, then we get this inequality. That when I take the p norm of the integral of this f with the y fixed, if I take the integral of this guy with respect to y, this is going to be the same thing as taking this norm and then taking the integral dv with respect to y. So what we're going to, the reason that we're going to be relying on this is up here. When we look at this guy, I can expand it. And now think about G as being one of these guys. Because again, G lives in LP and F lives in L1. So because this guy here is LP, when I pass this through, I can then rely on this statement here. Because when we get from the first part of the theorem that that the convolution lives in LP, so I can pass this through, and then what we notice is that the P norm is, this guy's has a variable x. So when I'm taking the P, this is on an x value function. F is in terms of y. So we end up with just the absolute value there because it's a constant that we can pull out. And then we notice that G of y is the same thing as the tau y of G. Because again, G has as a variable x, is with respect to x. So we get that the P norm of, that this second piece is going to become the P norm of tau y G. Then what we get is that this thing here, that's just, that's a constant. So we can pull this out of our integral. And now we're just taking the integral. Now we have tau y G P norm integral absolute value of fy dy. And what is that? We know that f lives in L1, so we know that this thing is, in fact, we know that that thing is finite. So that's just the definition of the one norm on f. So, and then we have that as a coefficient, tau y of G P norm. But again, as we've already proven in section 6.1, we can just drop the translation, because translations drop out of, we can just remove the P norms are translation invariant, so we drop that, and what we're left with is the inequality that we asked for. So, again, proof is a little bit outside the scope of the class. I did my best to cover it. If you're interested, Minkowski's inequality is theorem 619, so it's the one directly after this guy. Anyway, in the next video, we'll be starting back up with, where were we? We will be starting back up with proposition 8.8. Anyway, I will see you guys in a bit.